Fluorine is the most reactive element in existence, and for the longest time, I've really wanted to try making some. Hey everyone, welcome back to LabCoatz. Over the years, I've handled a lot of extreme chemicals on this channel, from the world's stinkiest to the spiciest,
Oh, that made worse.
and even some of the most corrosive. I love pushing the boundaries of what's possible in a home lab. That said, there are certain substances that I've had to avoid, and up until recently, fluorine was one of the big ones. To put it bluntly, fluorine is basically nightmare fuel for chemists. As the single most powerful oxidizer on the periodic table, it is said to ignite basically anything it touches, including traditionally non-flammable substances like water or asbestos. Even heavily fluorinated polymers like Teflon aren't safe. Given enough time and heat, they just get more fluorinated. And in addition to how immensely corrosive it is, fluorine is actually quite toxic. Its LD50 is eerily close to that of hydrogen cyanide, with significant exposure leading to unpleasant side effects, including hypocalcemia, skeletal fluorosis, and potentially cardiac arrest. With all these complications spelled out, it seems pretty obvious why people don't touch the stuff outside of the lab. Every single professional chemist I've spoken to has expressed only the utmost respect for fluorine, and plenty have gently encouraged me to pursue other projects. Even on the Science Madness forums, where you can find people making literal ounces of cyanide, nobody has dared to cross the line of do-it-yourself fluorine. So at this point, you all probably know what I'm about to say.
Fine. I'll do it myself.
Jokes aside, I've really been wanting to peel back some of the layers that surround this fascinating and frankly underrepresented element. So in this video, I will not only be showcasing every fluorine reaction I could film, but also deep diving into its properties, safety, a few misconceptions, and most importantly, how I actually managed to synthesize it. Believe me, things are going to get pretty insane. Now, full disclaimer, I am not a fluorine chemist. Everything I'm about to show was done at my own risk. I spent the last year doing research and significantly beefing up my safety equipment and PPE just for this project. Please do not attempt to replicate my work, unless you're a professional. But even then, maybe just leave fluorine alone. Alright, so I'm not a fluorine chemist, but I know someone who kinda is. You probably know him more for his work with high vacuum setups and alkali metal distillations, but Nicholas over at Advanced Tinkering has actually spent time working in a fluorine lab. And thankfully for me, he agreed to hop on a video call and talk about what handling it was really like, as well as some of the misconceptions that might surround it.
So, as a little disclaimer, I'm not an expert. I did this internship at the Fluorine Lab for 1 month, but I don't want to claim I'm an expert. Just so people don't think that I'm here the authority in fluorine chemistry. I'm not.
Okay, so where does fluorine kind of sit in terms of being a poison? How serious is it compared to like something else like cyanide or something that people generally think of as a poison?
Yeah, it's definitely up there, but I think it's hard to actually rank poisons. For example, how do you consider chronic exposure or basically accumulative poisoning from something? So there actually is a safe amount of fluorine you can be exposed to for long periods of time. Threshold limit value for fluorine is 1 ppm. That's basically the amount of fluorine you can be exposed to for a whole workday without any concerns. Should avoid it, but it is it's not necessarily dangerous if you can smell a little bit of fluorine.
Do you know how much it like bioaccumulates? Do you know like how much of an issue that is? Like if you're continuously exposed to it, obviously there will be some like accumulation over time. Do you know how bad that is compared to like lead or maybe mercury?
I don't think there's a real concern with accumulative toxicity with fluorine. I know that there are problems with fluorides and your teeth, for example, but I don't think there is a real comparable toxicity to lead or mercury or something like those chronically toxic substances. Yeah.
So if you're exposed to fluorine, the effects, the poisonous effects are mostly immediate.
Acute. Yeah. I mean, the actually toxic effects, also if you get HF on your hands, they can take a few hours or sometimes even a day or two to actually be noticeable. So there's this period of time, but no, it's not a bioaccumulative toxin, I would say. But I'm not a doctor, I'm not a toxologist, so I can't say for sure.
So I had one comment that was like, basically anything that fluorine touches in your lab or in your home, it's going to basically become poisonous or carcinogenic. Do you have a guess of how true that might be?
I don't think that's true. I mean, sure, you can't rule out that some organic compound that gets fluorinated becomes some kind of carcinogen, but I don't think that's a real concern. There's, of course, the danger that if something is moist and fluorine gets onto it, HF is formed, the HF stays there, and then you touch it. That's, of course, a concern. Sure, there could be a, carcinogen in those fluorinated organic compounds, but in a larger scope, I don't think these amounts actually matter.
Is there anything that you think I should know about fluorine? Is there any important things or maybe misconceptions that people might have that we haven't covered?
I mean, we have talked about some of the misconceptions, like the toxicity. I mean, it is highly toxic, but just because you can smell it doesn't mean
You're going to die.
immediate death. Yeah. The thing with fluorine is it has these two components. It's highly toxic and extremely reactive. So it's really hard to work with. I think it's one of those things where you have to have a lot of expertise I do not have, to judge different situations and know what you can do and you can't do. But working in a lab environment, a professional environment, you can work with fluorine completely safely. I mean, I've also talked to other chemists, and there are these urban legends about fluorine, just like cesium. I've heard so many urban legends about cesium and why people don't want to work with it. But if you're working in a professional environment with somebody who knows what he's doing, it's completely safe to work with it. Just like everything, it's about knowing what you're doing, having the right equipment, and being careful, I think.
All right, now that we're all a bit smarter, I think it's finally time for me to unveil how fluorine is actually made. Starting off with the two main chemical routes. The first route has actually been shown on YouTube before, by a channel called Chemical Force, and it basically involves heating heavily fluorinated salts like manganese trifluoride until they decompose. This definitely produces some fluorine, but the ingredients are quite expensive and the required temperatures are very high, so a lot of the fluorine simply reacts away. Overall, not a very useful process. The second chemical pathway is a lot more complex and wasteful, but it is theoretically easier to implement. Basically, if you react a large amount of hydrofluoric acid with potassium fluoride, hydrogen peroxide, and a bit of potassium permanganate, you get a golden precipitate of potassium hexafluoromanganate, which can be mixed with antimony pentafluoride to get a roughly 30% yield of fluorine. Needless to say, this method is also kind of impractical. Thankfully, there is a far superior alternative. From the very beginning, electrolysis has been the go-to pathway for making fluorine. If you don't know what electrolysis is, it's basically the process of using electricity to rip ionic molecules into their components. For a more detailed explanation, I recommend checking out Scrap Science. He has a lot of electrolysis content, and a full explanation video for all you real nerds out there. Industrially, this process is carried out on a solution of potassium fluoride in anhydrous hydrofluoric acid. So naturally, that was the method I decided to pursue first. The only issue I had was with the build material. Most sources suggest either nickel or steel for the electrolysis cell, and up until then, this was the best I could manage with those metals. You know your design is bad when the steel itself starts burning. Fortunately for me, JLC PCB offered to sponsor a video, and they were more than happy to 3D print me a custom cell made from solid 316 stainless steel. And let me tell ya, it came out looking amazing. While this is my first time formally partnering with them, I have used JLC PCB before, so this level of perfection wasn't exactly a surprise. I've used their PCB manufacturing services on pretty much every Tesla coil project I've shown on this channel, and they have always proven to be the most affordable option without sacrificing quality. Not only do they offer 1 to 4 layer PCB fabrication and assembly, but also 6 to 32 layers, starting at just $2 for a set of 5. That is just insane. And it's not the only thing JLC PCB can do. As I said, they also do 3D printing, offering various resins, plastics, and even 316 stainless steel, which is what I tried. And if that wasn't enough, they additionally perform custom CNC jobs, which is a service that I actually ended up employing later in this project. The sheer amount of materials, finishes, products, and options they offer for such a modest price is honestly mind-blowing. If you're a maker, professional, or anything in between, be sure to check them out using the links below. New users will also get a $60 coupon credit, which should come in quite handy with your first order. Seriously, if you have a project you're working on, check them out at jlcpcb.com. You won't regret it. Now, mixing up a solution of potassium and hydrogen fluoride was the plan, but when I actually tried distilling anhydrous HF, I ran into a few issues and never collected more than a few milliliters. It wasn't enough to make fluorine with, but it was just enough to synthesize a tiny bit of fluoroantimonic superacid, which was pretty cool. At the end of the day, I decided it was best to simply leave HF alone. It's just a huge pain to work with, and more importantly, it turned out to be completely unnecessary for making fluorine. After spending an ungodly amount of time searching, I eventually came across this document by L.M. Dennis, which gave me a fully detailed electrolytic process that only used potassium bifluoride. Apparently, excess hydrogen fluoride can be added to lower the melting point, but the author noted that this was unnecessary and could actually complicate things by making the mixture more prone to absorbing moisture. The paper was also gracious enough to specify a lot of other details that aren't usually discussed. For example, the presence of silicon, even in concentrations as low as 1%, can significantly stall fluorine production, as it tends to deposit on the electrodes as an insulating, glassy layer that has to be cleaned off. And, as suggested previously, water also inhibits fluorine production. As long as moisture is present, the cell will only generate oxygen, ozone, and maybe oxygen fluorides at the anode. Regarding Dennis' actual setup, it was basically just two copper pipes braced together into a V-shape with graphite electrodes secured and insulated by Bakelite plastic. I was kinda hoping that I could use the steel electrolyzer I ordered from JLC, but after a few tests, it became obvious that the molten bifluoride attacks steel quite readily. Bummer. So, for my first real attempt at making fluorine, I decided to assemble my own V-shaped setup using 1-inch copper pipes from my local Home Depot. I bought some supposedly pure graphite electrodes off Amazon and ordered a few kilos of potassium bifluoride from a chemical supplier. Following the paper, I baked the bifluoride at 130°C for 48 hours to remove any traces of moisture. And while that was happening, I decided to chemically treat the electrodes with molten sodium hydroxide and an array of other chemicals to remove silicon and other impurities from the surface. Despite my many preparations though, things didn't exactly go very well during my first test. On power-up, I did get a bit of crackling and popping from the cell, but there was absolutely no fluorine at the output. And worse yet, the current quickly dropped and the electrodes came out coated in both copper and a glassy residue. This told me two things. For one, the potassium bifluoride definitely contains silicon. Apparently, silicon is one of the major impurities in commercial fluoride salts, so the standard 98% stuff just wasn't good enough. And second of all, the combination of copper deposits and crackling noises revealed that my electrolysis chamber was probably too narrow, leading the copper vessel to participate in the electrolytic process. In other words, hydrogen was allowed to form on the fluorine side, which caused the crackling and absence of fluorine output. And on the hydrogen side, fluoride ions reacted with the copper to form copper fluoride, which was reduced back to copper at the cathode. Now, if you want to see a setup like this in action, go check out this video by Chemistry Easy. It's in Russian, but it does show off a functioning version of the Dennis cell in a proper lab, as well as a few interesting fluorine reactions. For me though, this is where I parted ways with the V-shape and started pursuing my own alternative. For the final design, I decided to draw inspiration from George Caddy's 1941 paper, which is honestly the single best resource I could find on fluorine electrolysis. Using this, and my barely passable understanding of SolidWorks, I designed a model with enough volume to fit half a kilo of potassium bifluoride, along with a port for temperature monitoring, a shallow copper skirt to isolate the fluorine, and a total of 4 anode ports to help me achieve the optimum current density of 0.15 amps per square centimeter. And, as a modern touch, I decided to use PTFE thread tape to insulate and seal the electrodes. Teflon isn't 100% safe from fluorine, but it is far better than the outdated Bakelite researchers originally used. Learning from my mistakes, I also purchased ultra-high purity potassium bifluoride and graphite electrodes, with the help of Microfilm Chemdelic, of course. You all better go like and subscribe to him, because this is like the third time he's helped me get chemicals for a project. Plus, his content is pretty awesome. As I hinted at earlier, the final electrolysis cell was CNC'd out of copper by JLC PCB, and after washing and drying it thoroughly, it finally seemed ready to make YouTube history. I loaded the cell up with the high purity Bifluoride, which, like before, had been dried for 48 hours at 130 C. The electrolyzer was then heated and maintained at 290 degrees Celsius, using a cheap Walmart hot plate with a whole lot of insulation. This temperature isn't strictly necessary, but it did seem to work well for my setup. Eventually, all the bifluoride melted, and the top of the cell was placed on. The positive end of my benchtop power supply was connected to the 4 fluorine electrodes, and the negative was hooked up to the lone hydrogen electrode. Again, these electrodes were all sealed and insulated from the copper body by Teflon. To see if I was actually getting fluorine, I decided to place a piece of paper towel at the output, which I figured would ignite pretty easily. So, with everything set up and my fingers crossed, I lowered my fume hood and flicked on the power. At first, nothing really seemed to happen. I heard a bit of the same crackling noise, and the current did drop a little, so I was honestly expecting yet another round of failures. After about 15 seconds though, I saw something that actually looked like smoke. The paper wasn't charring, but there were definitely white fumes coming from the electrolyzer. This seriously got my hopes up, so I decided to try running an actual reaction. I loaded a few pearls of iodine into a test tube, stuck it on the outlet, and prayed that something interesting would happen. And thankfully, something did. The iodine melted and produced a brownish deposit of iodine monofluoride, which rapidly dissociated and reacted further to produce a clear liquid that was almost certainly iodine pentafluoride. And upon heating the mixture, things got even crazier. The iodine vapor actually caught fire. No other gaseous element has this kind of reaction with iodine, leading me to conclude that yes, I had in fact produced fluorine in my garage.
Ladies and gentlemen, we got him.
Now, just in case a few of you are still skeptical, this is a solution of calcium chloride in water. In the presence of fluorine, it should react to form a white precipitate of calcium fluoride. And upon powering up the machine, that's exactly what happened. There are other gases that could produce this effect, such as hydrogen fluoride, but essentially none have the ability to ignite a powerful oxidizer like iodine. So yeah, we've definitely got fluorine here. I'd say it's time to try a few reactions. And by a few, I mean roughly 20. First off, I really wanted to try phosphorus. This was the main test I used during my first set of failed trials, and I really wanted to give it a fair shot at working. Naturally, it went up in flames immediately. In hindsight, doing this particular reaction wasn't my best decision, since the phosphorus fluorides it produces are actually quite toxic. At the same time though, only a few milligrams were actually formed, and the moisture in the air inevitably neutralized all of it. After phosphorus, I figured it might be fun to try out a few solvents, starting with one that I actually have quite a bit of history with: acetone. Over the years, I've managed to Frankenstein this unassuming little ketone into some pretty foul-smelling chemicals, including the legendary thioacetone and its much stinkier selenium analog. I even mixed it with a superacid once, which honestly seems pretty tame after seeing it touch fluorine. Like me, you might have been expecting a few fiery puffs, but I guess violent detonations are more fluorine style. Now, here's a liquid that I've always wanted to see tested: water. According to legend, water readily ignites under fluorine, but when I tried the reaction in an open beaker, all I got was a bit of smoke. So was this simply one of the tall tales of fluorine chemistry? Nope. I have no clue how the test tube survived that. It was absolutely deafening. And would you look at that, an actual flame. I guess water really does burn under fluorine, just a bit more explosively than I first imagined. Looking for an even more violent explosion, I tried a few drops of nitromethane, which surprisingly didn't ignite until I got the mixture boiling. Once it caught though, it did give a nice snap, followed by a beautiful white flame as I continued heating. This was pretty interesting, but it wasn't my favorite solvent. That title goes to Dichloromethane. There's just something about burning a non-flammable liquid that feels cool. Comment what you think as the clip plays out though. I don't know, there's just something cool about that. Now, before we move up to the large-scale tests, let me show off a few chemically interesting reactions. This is sodium bromide. Plenty of people requested that I react fluorine with bromine, and this was my roundabout way of making that happen. Passing fluorine over sodium bromide caused the bromine to crash out, and once it was in the vapor phase, things started to get interesting. As a gas in the presence of excess fluorine, the bromine reacts further, producing a pale mixture of bromine trifluoride and bromine pentafluoride. This stuff is basically the slightly more stable version of chlorine trifluoride, so successfully making it honestly felt pretty cool. As you'd expect though, it all reacted with the glass, and I never got to collect any of it. Another interesting element that reacted with fluorine actually ended up being vanadium. I picked it because of its tendency to produce colorful salts, and let me tell ya, I wasn't disappointed. Heating the sample caused a variety of vanadium fluorides to be produced, which reacted with the hot glass to form an orangish layer of vanadium oxytrifluoride. Where the glass was cooler though, yellowish bands of vanadium tetrafluoride began to deposit and sublimate their way up to the fluorine inlet. Here, the tetrafluoride reacted even further, producing the clear liquid vanadium pentafluoride, the most halogenated form of vanadium that currently exists. Also, some vanadium caught fire, which was pretty cool to watch. Following vanadium, I really wanted to try samarium. I knew it didn't have any colorful salts, but if chemical force has taught me anything, it's that samarium is fun to react with strong oxidizers. It did react, producing a rather showy eruption of sparks, but my fluorine flow was a bit too weak for it to really go crazy. All it really did was glow red hot and burn a little after the flare-up. Alright, no more fooling around. It's time for the big reactions. For these, I hooked up an Erlenmeyer flask to the outlet of my electrolyzer and let it run for several minutes to collect the fluorine. If you're wondering why on earth I would use glass, it turns out that fluorine's reaction with it is actually very slow. So if you work quickly and use dry equipment, you can kind of get away with it. When I filled the flask for the first time, I was kind of hoping that I'd get to see the color of fluorine. But alas, the color is actually quite faint, making it almost invisible in small dilute amounts. There are still ways of telling it's there though. For example, you can drop in a spoonful of sulfur. I absolutely love that ghostly blue flame. It's hard to convey the intensity of the fire though, so here it is again with the lights out. Okay, this might be the intrusive thoughts talking, but I've always wondered, what would happen if you put your finger in that position? Well, now that I have a working electrolyzer, I intend to find out. Just not with my finger. Instead, I'll be using disposable gloves and some cold turkey. First up, a clipping from the vinyl gloves that I usually wear during my experiments. Shockingly, the glove seems to have survived pretty well. So I guess vinyl does provide at least some protection against fluorine. And to prove this flask wasn't just a dud, here's a bit of diethylamine. Very cool. Now, let's try the turkey. That's mildly terrifying. Just look at the surface. The fluorine basically converted all of the moisture in the meat into hydrofluoric acid, which not only dehydrated the surface, but also left it looking unnaturally pale. Makes me pretty grateful for all the PPE I invested in. Let's try some other common materials. What would happen if the cotton in your shirt or lab coat suddenly came into contact with fluorine? Apparently nothing good. And what would happen if you accidentally swapped your fluorine-resistant plastic with, I don't know, Styrofoam? Okay, I might have just been having some fun there. This next reaction was also for fun, and it actually wound up being my favorite overall. The reaction between fluorine gas and regular wood. That pause and comedic pop as the wood burst into flames gets me every time. So far, I've shown a lot of fuels burning in an atmosphere of fluorine. But what happens if we play an Uno reverse and burn fluorine in an atmosphere of fuel? Specifically, butane. Okay, I have to admit that I took a bit of inspiration from Cody's lab, who tried burning oxygen in an atmosphere of propane several years ago. This is basically the terrifying step up from that, and best of all, it doesn't even require an ignition source. Now, I'm sure that some of you are probably expecting this to simply fluorinate the butane into perfluorobutane, which is an extremely dense gas that can make your voice sound really deep. Coincidentally, Cody's lab also has a video showing this. Unfortunately though, concentrated fluorine isn't really useful for this purpose, or for a lot of organic fluorinations honestly. It just ignites things way too easily, including this fan favorite, magnesium powder. That was pretty satisfying. Let's see what happens if we replace magnesium with an even more reactive metal, like maybe sodium. Gotta be honest, I was expecting something a bit more dramatic. I'm guessing the bulk solid just passivated way too quickly for it to really take off. That, or I didn't add enough fluorine. Either way, I tried again under a constant flow of fluorine, with heating from my blowtorch, but it still refused to fully ignite. In an older video, Now Red actually had a similar issue with chlorine, so I guess this outcome isn't totally crazy. Still, I can't let my final reaction be that pitiful. Fortunately, I had some Toluene on hand, and figured it might be fun to mix with one of the world's strongest oxidizers. You've gotta love those orangey-yellow flames dancing around inside the flask. Okay, since you've all been so well behaved, here's a quick bonus reaction. I know some of you are probably wondering what happens when you mix fluorine with hydrogen. Well, I'm happy to say that I did capture them reacting. Just not intentionally. Once or twice, a large bubble of gas passed over to the wrong side of the electrolyzer, resulting in a few fairly loud explosions. Thankfully, these never had any real force behind them, and all they really did was startle me. At this point, I've shown pretty much every reaction I ran with fluorine. So now, there's really only one thing left for me to cover: the smell. I've documented a lot of chemical smells on this channel, both intentionally and unintentionally, including a few fairly toxic ones like phosphoryl chloride and hydrogen selenide. Despite my prior experience touching noses with death though, I wasn't about to deliberately inhale fluorine. Fortunately for me though, I knew somebody who already had.
Anyway, we're just having a Zoom call while hanging out at home in LabCoatz.
This is what YouTubers do, I guess.
Yeah, of course. Yeah. Oh, and there's my cat. I'll let him in. I'm great at staying on topic, by the way, obviously. What are you doing? Well, yeah, okay. Yeah, I'm on an official Zoom call.
I guess I should probably ask the question that everyone's wondering, at least from me, the guy who smells selenium and other stuff. So, what, from your experience, you mentioned it on your own video, but what does fluorine smell like, at least to you?
I was expecting to smell a lot like chlorine, that kind of really sharp, very synthetic, like aggressive, sharp smell. But for me, it wasn't like that. It was obviously still very chemically, but it was a lot more natural, kind of like, I said it was even sort of cabbagey. It wasn't like earthy, but it was like kind of greeny or like lawn clippings more. So not the smell of lawn clippings, but that kind of feeling of that kind of softness of like, greenery rather than that sort of attacking you smell.
Yeah. Well, I'm sure it's different whenever it's like pure fluorine. Like
obviously, if you're if you're dying, it probably smells like you're dying. But at low concentrations, you kind of are expecting such a harsh chemical to smell like your cells are actively dying. But it wasn't actually that unpleasant, really. And it wasn't really like nitrogen dioxide or chlorine or one of those ones that's really less of a smell and more of just a sharp feeling of pain.
Just pain.
Yeah. It was kind of discernible as like, oh, this is kind of a gas that you can smell and it kind of has this quite distinct odor to it.
I was kind of curious since you smelled it, did it resemble any of the other halogens more than the others? Like, because fluorine, chlorine, iodine, they're all sort of unique, right? They're a little bit different.
Yeah. I suppose it's that sort of the mustiness of bromine. I suppose if you're comparing chlorine, bromine, and iodine, you would say bromine's sort of the musty one in a sense. Like chlorine is sharp, iodine's very hygienic, very sort of sickly in a way, sweet, whereas bromine's kind of in the middle there. I mean, I'm so bad at describing smells, but it's kind of thick and wide, let's say, rather than sharp. And that is sort of similar to fluorine, but there's no way you would get them confused. I mean, bromine is quite unpleasant. It's not like painful, but it's quite unsettling, I suppose, in its smell, and that's not what I got from fluorine. Yeah, there's not really a nice trend in there. Each of the halogens is quite distinct. Yeah, for sure.
Alright, so I guess in low doses, fluorine basically smells like a more natural version of bromine or chlorine, which is honestly about what I expected. There was one point while I was cleaning up a fluorine reaction and smelled something vaguely chlorine-like, but it was a bit too weak for me to really analyze it. Still, pretty interesting. Also, shout out to Genius Lab Gear. By sheer coincidence, they sent both me and Tom custom lab coats, which we both wore during the segment. Although I think Tom switched back to his original at some point. Their products are super high quality, and if you want to pick one up for yourself, feel free to check out my affiliate link in the video description. So, that's just about the extent of my fluorine experience. In the months to come, both Advanced Tinkering and Elias Experiments will be releasing fluorine videos of their own, so if you find yourself craving more unique fluorine content, rest assured more's on the way. At this point, I'd like to thank everyone who's a part of this achievement, especially Tom and Nicholas. It was super cool talking with them for the first time, and I definitely look forward to chatting with them some more in the future. Who knows, maybe one day we'll all get together and do a more official collaboration. One can dream, right? Additionally, I would like to again thank Micah from Chemdelic for helping me obtain the reagents I needed, and JLC PCB for being patient and producing the various electrolysis cells that I went through. And of course, all of my Patreon supporters, because they're the ones who truly make projects like this possible. To all of my subscribers, thank you all for believing in me and getting LabCoatz past 100,000 subs. This has been one wild journey, and I can't wait to bring you even better chemistry content in the years to come. Remember to like, share, and subscribe, and I'll catch you next time. LabCoatz out.